Hi, we are going to be looking at moment distribution method, which is one of the methods that is used to find the internal forces in statically indeterminate structures. The methods or the steps used in calculations as follows. First of all, you need to find the linear bending stiffness I, which is equal to EI divided by the length of the span. The next, we need to find the endpoint moments, that is from the table that has got spans having different types of loading. Then besides that, we need to calculate the bending stiffness S. Then after which we come and find the summation of the bending stiffnesses at a particular point. After doing that, we need to find the distribution factor mu, and we also need to find the carryover factor C. The next step after that, we need to find the moment to be distributed, and then lastly we draw the bending moment diagram, having gone through the first 4 steps successfully. So next, by means of examples, we are going to be looking at how these steps are put into use to find the internal forces of statical indeterminate structures. But before that, we need to first look at some of the basic spans that we use in this method of calculation. These spans are similar to those that are given in the displacement method. One of them is a structure of that kind. Let's assume that this part is part A, then this is part B. Then we also have another one that is having such a kind of support. Then besides that, let's say we also have this one here like this, and then lastly we consider this one that is fixed at a rigid support and the other side is left hanging. So all of them are having A and B. So the linear stiffnesses of all these spans are given as below. So for the first case, our linear stiffness SAB is given by 4I. That is in a case where we have, this is I, in a case where we have both ends fixed. Then for the next one, our bending stiffness is given by SAB is equal to 3I. That is for a span that has got a fixed end, a fixed rigid end, and then it has got a hinge joint at the other. Then for the next one, our bending stiffness S is given by I. And then for the last one here, our bending stiffness is given by SAB is equal to 0. So these values of the bending stiffnesses need to be memorized by each individual because they are the basis of our calculations in moment distribution method. Usually, for a case where we have got a rigid support at both ends A and B, one of them will be carrying a value of 4I, then the other one would be carrying a value of 2I. Then for a case where one of them is a rigid support and one of them is a hinge, one of them carries a value of 3I, then at the other hinge it holds a value of I. Then for this one here we shall be having I, and then at this one we shall be having negative I, like that. Next we come and see how we evaluate for our C, that is the carryover factor. So from the beams that we have above, I'm going to add on something on the diagrams. Like for a case where we have a rigid support and a rigid support, this one usually also has a value of 4I, then one of them carries 2I. Then in a case where we do have a hinge and a fixed support, one would be carrying 3I, one doesn't hold any. Like at the hinge, it takes on a value of 0. Then for such a structure, here we shall be having I, then this would be giving us negative of I. Our C is given by the ratio of, okay, let me just use M m small divided by m big. So this is B. Yeah, so starting with our very first span, our CAB would be equal to a 2i divided by 4i. We would be having a half. Then for the next, our CAB would be equal to a 0, smallest, then divided by the biggest, we would be getting a 0. Then for the next one, CAB would be equaling to, that is negative I divided by I. That gives us a negative 1, like that. These values here are values that we need to memorize because they are commonly used in our evaluation of questions involving the moment distribution. And then next, the other thing that we need to talk about is how to evaluate our distribution factor. So our distribution factor, we said, is given by mu. So mu is given by the S on a particular span, then divided by the summation of S at a particular point. Yeah, so we shall see how we calculate for all these stuffs by means of an example. But before you move on to the example, I want us to look at the what? I want us to have a look at the table, that was spoken above, like in point 2, that to find the endpoint moments, we need to use what? We need to use the tables of this format here, like as in we do have those 4 spans under different kinds of loadings. Then then for every span, they do give us the moment that is at a particular end. So for example, a rigid support at A and rigid support at B and distributed load, the endpoint moments at the endpoint moment at point A would be negative QL squared divided by 12. Then the one at the opposite end, that is end B, would be given by QL squared divided by 12. Yeah. So depending on the span that you have in a question, you simply come and refer to these tables here. But mainly, the ones that we are going to be considering are these ones that have been marked. This span number 1, then number 4, number 6, number 10, number 12, and then number 14. These are the spans that we are going to be using much in our examples. So let's assume we've been given a question as shown, and then we've been given a beam that has got 2 spans, that is span AB, BC, of span length 6 meters each, and then the loadings are indicated above, and then we are required to find the what? So we are required to draw the bending moment diagram. So from what we had said, we said that when you're given such a question where we are required to use the moment distribution method to draw the bending moment diagram or find the internal forces, the first step is we need to find the linear bending stiffness, that is I, isn't it? So in this question here, we are lucky that the linear bending stiffnesses have been given. Like that is this one here, they have been given, so all of them share a common linear stiffness. So that means that that part has already been catered for. Then we move on to the next. Our next step was requiring us to find the value of the endpoint moments. So as you prepare to find the value of the endpoint moments, what we always first have to do is to first of all add a clamp at the spans that are in the middle of the beam. So for all the hinges except these ones, like except those at the extreme end, like for this case we have A and C at the extreme end, then whatsoever support that is given in the system, say for example here we have B, yeah, at each of them we have to add a what? We have to add a clamp. This one here becomes a fixed support. So when this becomes a fixed support, we come and extract out the corresponding spans from the system. So that means that the above question can be reduced to a scenario that has got these 2 spans. So we say that B becomes a fixed end. So here we're having A, and then here we're having B. then this is under a load of what? Of 20. Then our next span would be, we have a fixed end at B, and then we are having this hinge at a point C like that. So our system that has been given above can be reduced to what? To this one here. Okay, so after we do that, now we begin finding our endpoint moments. We take a look at the spans that we have come up with, and then we move on to the tables and try to look out for the spans, and then see the formulas that have been given for the corresponding endpoint moments. Now if you come to our table that has got the spans with their corresponding end moments and look keenly, we shall discover that our first span was two ends fixed with a rigid support, and then having a concentrated load acting in the middle of it. So that one there would be this scenario here, this one here, of which our endpoint moments at a point A, the moment would be given by negative FPL divided by 8. Then at the opposite side B, it's given by FPL divided by 8. So we move on and calculate for the endpoint moment using that. For our first span, we say that our endpoint moment M at point A, MAB, is equivalent to negative 1 over 8 FPL. So our FP is 20, and then our L, the entire length of the span is 6. So this one here would be giving us a value of negative 15 kilonewtons meter. Then the one at the opposite end, that is MBA, was of a value of 1 over 8 FPL. So simply they just vary by a sign. This one here carries on a value of 15 kilonewton meter. So for the second one, we see that it is of the category number 6. One end is fixed, and then one end has got a hinge. And then the moment, we know that the hinge does not carry any moment, so the moment at the fixed end will be given by negative QL squared over 8. So we say that our endpoint moment M, so this case will be MBC. MBC is equivalent to negative 1 over 8 QL squared. So this one here would be giving us a value of negative 90 kilonewton meter. Then for our next part, we need to come and find our bending stiffnesses. So I will say that for the bending stiffness, we need to refer to these values that we had given before. So we see that in a case where we have got a fixed end and a fixed end, our bending stiffness is given by a value of 4i. Then in a case where we are having a fixed end with a hinge, our value of bending stiffness is given by 3i. So that's for the first category. Then we come and find the bending stiffness. For the first span, our S, it will be like SBA would be equal to 4i, as in, like, usually we do consider it from the point where we have the clamp. So if at all our clamp was at a point B, so our bending stiffness would be SBA. Then for the sake of the second span, we are clamping it at B, then we are looking at the span on towards the side C. So we shall be having our bending stiffness given by SBC. It would be equal to a value of, for this kind of a support, where we have one end rigid and then the other end having a hinge, we say that the value is given by a 3i, like that. After finding our bending stiffness, next we get the summation of the bending stiffnesses at the point. So for this case, our summation, we only have one single point, that is point B. So we are going to find the summation of the bending stiffness, that is at point B, would be equal to 4I plus 3I. This gives us a value of 7I, like that. Now, after finding the bending stiffnesses and the summation, we can now move on to the next step of finding the what? Of finding the distribution factor. So the distribution factor, if you remember, we say that it's equal to mu. Distribution factor mu is equal to S, that is the bending stiffness, divided by the summation of the bending stiffness. For this case, since we are dealing with only point B, our distribution factors would be given by, say we are dealing with what? With the section, with the span BA first. So we shall calculate it as follows. Mu BA would be equivalent to our SBA, which is 4I divided by the summation, which is 7I. This gives us a value of 4 over 7. Then we find that of BC. So mu BC would be equivalent to SBC, which is 3I, then divided by summation SB, which is 7I. This gives us a value of 3 over 7. So these are the two values that we have for our distribution factor. Then the next step from our steps of calculation is supposed to be to find the C, which is the carryover factor. But then these ones here, we can just cram them. Like we say that if in case we are having two rigid supports, like in this first case here, our carrying factor would be a half. Then if in case we do have a fixed end on one side and then a hinge on one side, the carrying factor is given by a 0. Then when we have this case here, our carrying factor is a -1. So that means that for the sake of this example that we are dealing with, for the first span AB, this one that has got a concentrated load, our carrying factor would be a half. Then for this one here, we won't be having a carrying factor, it would be a 0. So we can note it down that the carrying factor C AB would be equal to a half. Then the carrying factor C BC is equal to a 0. So after doing that, we say that the next part is supposed to be finding the moment that is to be distributed. Now to do this, we are first going to draw the span of our beam and then indicate the end moments that we had calculated onto each individual end. So our beam was as follows. We do have a fixed end, then we do have a hinge support in the middle, and then also a hinge support at this extreme end. Then from our calculations, we had found our end supports as follows. Okay, at the first end, that is end A, we had a value of -15. Then at point B, we had a value of +15, and then a -90. That is for the sake of MBC. Then for this one, we know it's supposed to be a 0, as in the value for MAB is -15, MBA is 15, then MBC -90, and then 0. Those are the values that we got at this upper calculation here. Yeah, these values here are the endpoint moments. So having done that, now to get the moment to be distributed, we do pull out the hinge that is in the middle, as we had described that, not these extreme ones, but now we pick up a point like this. So in this example, we only had one support that was added to the system. But then if there are several, we first begin by calculating the moment to be distributed that has got the highest value. But we shall see that when we get to it. Let's first begin with this case. So what I forgot to say was that in these calculations, we have got a sign convention that a clockwise moment is positive and then the anti-clockwise moment is negative. So for this case, we do pull out the hinge, that is the hinge B. So at point B, the moment to be distributed that we want to find, we give the moment we want to find a clockwise direction, because clockwise is positive, then we label it M. Then now, like at point B, we've got two moments that are acting. We've got the moment of value of 15 that is positive. That means that it is acting in the clockwise direction. The negative 90, that means the 90 is acting in the anti-clockwise. But as we calculate the moment to be distributed, when we are picking these two moments and adding them onto this figure here, we draw them with the opposite signs on them. So if this one here was in clockwise, here we come and indicate it in the opposite direction, that is in the anti-clockwise, as in making it negative. So this becomes a 15. Then this one here was a 90, that is the moment MBC. This is B, this is C, and then this is A. MBC was negative 90, so we draw it in a clockwise direction instead, like we use it as a positive, so it takes a clockwise 90. Therefore, my value of M would be equivalent to, that would be 15, 15 minus 90. This gives me a value of negative 75. But now, like the moment to be distributed, let me call it M D, the moment to be distributed, it's equal to negative of M. So this would be equal to 75 kilonewton meter. So this is the moment that we need to distribute. So having found the moment to be distributed, now next we move on and then go on with the process of drawing our pending moment diagram. Then we have calculated for our distribution factors, and then we found them as follows. So the distribution factors are being distributed at a point what? Are being distributed at a point B. And then our factors were, just moving up to check on the factors, we had MBA, that is on this side. MBA was 4/7. Then on the other side, MBC was a 3/7, like that. Then our moment to be distributed, the MD, we come and write it on top here, 75. Then after doing that, we also come and re-indicate the 9-point moments. Here we had a negative 15, here we had a positive 15, then here we had a negative 90, then here we had a 0. So having demarcated all that, now we begin distributing our moment. So we do get this moment to be distributed, then we multiply it by the distribution factor. So if at all I'm to begin with the left hand side, I take the 4/7, times 75. It will be giving me a value of 42.9. Then when I take the 3/7 times the 75, I get a value of 32.1 here. Then we say that on a part where we are having a fixed support, like the small span that we took out by putting a clamp at B, gave us a section AB with a fixed end here. Then we say that this one here has got a carryover factor over half. So we come and multiply this by a half and we carry over times a half. Then here we shall be carrying over a value of, that would be 21.4, like that. So for the sake of a number with only one support in the middle of a span, we only, just by distributing the moment once can give us a fairly accurate answer. So having done that, now we come and add up the moments at each point. So when you add up the moments at point C, we only have a 0. So here we have our final moment as a 0 at point C. Then at point B on the right hand side, we have negative 90 plus what? Plus 32.1. We get a value of negative 57.9. Then when we come to the left hand side of point B, we have 15 plus 42.9. We come up with a value of 57.9, like that. Then now when you come to point A, we have negative 15 plus 21.4. That gives us a value of 6.5. Having found these values here, we can now move on and draw our bending moment diagram. And then the process of drawing is as follows. At this point here, okay, now it's always good to pull out the hinges and then first determine the direction of the moments before we draw the final diagram. Then for the sake of this one here, yeah, okay, for the sake, let me just do it like that, yeah. So for the sake of our point A, we saw that the moment that we came up with was what was 65. That was in the clockwise direction since it's positive. But then as we are drawing, we still change the sign. We multiply it by negative. So this becomes a what? We draw it in the anti-clockwise direction. So it becomes an S6.5 like that. As in we draw it opposite to this. This one was positive, it was supposed to be clockwise, but then when we are drawing it on the bending moment diagram, we do give it a what? We do give it a positive sign. So now when I come to point B on the left hand side, I had a value of what? I had a value of 57.9 in the clockwise direction, but then when I draw it on the left hand side, I draw it in the anti-clockwise. Since this is positive, on the bending moment diagram it takes on a value of a negative, like that. This becomes a 57.9, like that. Then when I come to the right hand side, value of 57.9, but then in the clockwise direction, because this one was supposed to be anti-clockwise, usually negative, but then we said we come and draw it in the opposite side. Then at this hinge at point C, we have it as a 0, so we don't indicate anything. Now having done that, now we come and draw. At our point A, we have a value of what? Of 6.5, and then it is the upper part that is under tension. So let's say our 6.9 is that high. Then when you come to point B, we have a value of 57.9, and then we can observe that it is the upper part that is under tension, so you draw it up. Then at this point it's a 0, yeah. So if in case like we never had forces acting on the various spans of the beam, that would imply that we would simply draw straight lines connecting towards them. But then from the question, we can observe that on the first span, that is from here up to here, on the part AB we have a concentrated load of magnitude 20. Then the part BC we have a distributed load of magnitude 20. So therefore, what we do is to first connect up the span, the endpoint values using dotted lines like that. So we come and connect it with a dotted line. So because there is action of a distributed load, we know that the action of a concentrated load, we know that a concentrated load would be having such a bending moment diagram with a peak value of 1/4 FPL. So we come and superpose that at this place like that, giving us that as our final shape. Then if you look at the part BC, it also had the action of a distributed load, so we first come and connect this place using dotted lines. Then a distributed load has a bending moment diagram of that nature, so this side you also come and connect it like that. And then our values on the diagram would be, here we're having 6.5, then here we're having a value of 57.9, and then here we're having a 0. So the 0 I can just leave it without indicating it. So that is how we draw the bending moment diagram using the moment distribution. Then we're moving for our next example. As the first one, with this one we're also required to find the to draw the bending moment diagram, or the same question can be stated as find the internal forces in the structure. So mainly when they ask you that, you would need to find the bending moment and then the shear forces and the likes. But for this case, we shall just mind. But for our case, we are just going to be drawing the bending moment diagram. So let us look at the differences between this question and the other one. For the other question, we had been given the linear. For the previous question, they had given us the linear bending stiffness small I, but for this one it hasn't been given. Yeah, like in this case we have just been given the EI. Here it's a 1, then for the next span it's a 2, then for here it's a 1. So you can see that it's not a uniform value. So that means that we shall have to calculate the bending stiffness, the linear bending stiffness for each section. But first, if you remember, we said that before doing any calculation, we first of all distribute the entire structure into small spans. So for this case, what we do, we can apply clamps at point B, then at point C. Like the clamps are applied at the supports that are not the extreme supports, as in like not these end supports like this one and this one. We only clamp the supports that are in the middle. So after clamping them, that means we have a structure that comes out like having two spans, and then the first span that we shall be having would be the span AB, that would be of this nature here, like this. Let me change my ink. We shall be having the span AB, A, B, under the action of the distributed load of magnitude 20. Then we shall be having the span BC under the action of a concentrated load of magnitude 100. This is BC. And then lastly, we shall be having the span CD under the action of no force. Yeah. The one thing you should remember is that each point that has been clamped, when we are drawing the respective spans, the respective individual spans, like we do represent like the areas which are clamped are represented by a rigid support, like point B. So you see that at point B we give all the sections of the span a rigid support. Yeah, likewise at point C. So after doing that, now we can move on and find our what? Our linear stiffness. Okay. So we know that our linear bending stiffness, small I, linear bending stiffness, linear bending stiffness, small I is given by a value, or is given by the formula, by formula EI over the length of the span. Yeah. So if we are to begin with the span AB, we would be having our IAB as like IAB is equal to IBC. So IAB is equivalent to IBA. So if we observe, we see that if you also observe another diagram, we see that the span AB and span CD have got an equal value of the EI and then an equal value of length, isn't it? So their linear stiffnesses will be the same. So IAB would be equivalent to ICD, which would be equal to, our EI is a 1, then the length is what? Is 6. So therefore our EI would be equivalent to 1 over 6. Then the one in the middle, the IBC, would be equivalent to the EI is 2, then divided by the length is 8. This gives us a value of a quarter, like that. So having found our linear bending stiffness, next we move on and calculate for the endpoint moments. So next we said we come and find the endpoint end point moment. So the endpoint moment, if let's say we are to begin with our first band, AB, that is the span AB, this one here, we would be having, like we see that it is at the action of two rigid supports. So we move back to our table and then we look for the rigid support that is being acted upon by a concentrated force. We see that it is this first case here, case number 1, and then the endpoint moments are given by at point A it's negative 12 QL squared divided by 12, then at point B it's QL squared divided by 12. So knowing that, we come and do the corresponding calculations. So our MAB is given by negative Q L squared divided by 12. So this one here would be giving us, our Q is a 20, then L was 6, so that is 20 times 36 divided by 12. That gives us a negative 60. Then the MBA just varies by sign, so this becomes a positive 60. Then you move on to our next span, that is the span BC. So for the span BC, we have the same kind of a support, like two rigid supports, but yeah, two rigid supports, but under the action of a concentrated load of 100. So we come and look for that here. Two rigid supports, this one and this one, under the action of a concentrated load. Then we see that the endpoint moment are given by negative FPL divided by 8. Then the other one is just with a difference of a sign. So we move on and calculate for that too. Okay, so our MBC would be equivalent to, it was negative FPL divided by 8. So this one here gives us negative 100 times 8 divided by 8. That gives us a negative 100, like that. So the MCB just differs by negative sign, so this becomes 100. Then for the sake of our last span, like we see that we have a rigid support on one side, then a hinge joint at point D, but then since we have no loading, it won't be carrying any moment on it, so the moment on it will be equal to 0. Now after we've done that, the next is now to come and calculate for the bending stiffness. So with the idea of what we had looked at before, and like we say that in case where we are having a fixed end, say like two rigid supports, and then let's say B end was clamped, so our bending stiffness, we say that in that case becomes a 4i, that's the SBA would be a 4i. Then likewise, when we come to this side, it's still the same scenario. If let's say we are dealing with it in difference from point B to point C, our bending stiffness would be what? Would still be a 4i, as in like, yeah, let's look at it in terms of this beam. So we need to find the bending stiffness. The bending stiffnesses of these sections here, like one towards the sideward. Okay, just a moment. Okay, the bending stiffnesses we need to find as follows. Like one of them is to the side BA, like from B towards A, thus it would be SBA. Then the one from B to C would be SBC. Then besides that, we also need to find the one that of that one at point C. So when you come and look at point C, we would be having one that is SCB, and then the other one would be SCD, like that. So we move on and then we see how we go on with these ones here. So if let's say we do clamp point B, looking at point B, we would be having that is, we are dealing with point what? Let me use a different ink. Dealing with point B, our SBA would be having SBA, as we had shown, the direction from B towards A would be equivalent to, we say that would be 4I BA. So it would be 4 times IBA. This would be equal to 4 times our IBA was equivalent to 1 over 6. This gives us a value of 0.06, sorry, a value of 0.12 over 3, 0.667. Then when you move on to the next one, that is still at point B, we've got that of BCS. BC, this would be equivalent to, it is still like moving from a fixed end to a fixed end, as like BC, from fixed to fixed, so it also remains a 4I. But then for this case, it will be 4, it could be a 4I, 4I what? 4I BC. This would be equal to 4 times IBC was 1 over 4. This gives us a 1. Then after doing that, we come and sum them up, and then we get summation of S at point B. This would be equivalent to 0.667 plus 1, that gives us 1.667. Then we come and deal with point C. So for the sake of C, we are having for the point C, we shall be having the bending stiffness that moves from C to B, then the one of C to D. And then these ones, the values would be as follows. So when I deal with the first one, let's say SCB, that is from C towards B, this would be equivalent to C toward, from C towards B, it's from fixed to fixed, that would be equivalent to 4I B C. This would be equal to 4 times 1 over 4. That would be equal to a 1. Then when you come and look at the SCD, that is from C then towards D, I would say that that one there is given by 3ICD. That would be equal to 3 times 1 over 6. That would be equivalent to 0.5, like that. So having found our bending stiffnesses, the next is to now come and find our distribution factors. We had said that the distribution factor mu is given by the S at a point, then divided by the summation of the S. So if at all we are to begin with point B, we begin with the mu BA. This would be equivalent to SBA, then divide by summation S at B. This would be equivalent to SBA, that is 0.667, then divide by 1.667. That would be equal to 0.4. Like that. It will be equal to a 0.4. Then when you go to mu BC, this would be equal to SBC divided by summation of S at B. That would be equivalent to 1 divided by 1.667, giving us SBC divided by summation SB. That is 1 divided by 1.667. That gives us a value of 0.6. Then we move on to point C. So point C, we shall be having mu CB, that would be equal to SCB, then divide by summation SCB, like that, which is equal to 1 divided by summation SC. That would be equal to 1 plus 0.5, which is equal to 1.5. So we take so our mu BC, we would say that would be equal to mu CB divided by summation of S, sorry, it's supposed to be S at C. Summation of SC, like that, so divided by 1.5. This gives us a value of 0.667, like that, 0.667. Then we go to mu CD, this is equal to SCD, then divide by summation of SC, this is equal to 0.5 divided by 1.5. That's equivalent to 0.333, like that. So having found our distribution factor, next is now to find the moment that is to be distributed. So we'll say that first find them, before you begin to find the moment to be distributed, we first need to indicate the endpoint moments onto the structure that we are to deal with. So for this case, we go back and we get these moments here which we calculated. These ones are the endpoint moments here. These ones, we have a m at point A, we have negative 60. At point B, we have a 60. Then at point B on the right, that is BC, MBC at negative 100. Then on the left we have 100. Then on the right we have 100. So we come and we get those values, and then we come and put them. So as we had seen from above, at point A we said our MAB was negative 60, then MBA was 60, then MBC was negative 100, then we had MCB as 100, and then on the other side we had a 0. So after doing that, now we compare these values at these two supports, support B and then support C. At support B, when I add up the two, I come up with a value of what? With a value of negative 40, while at point C, when I add them up, I come up with a value of 100. So that implies that the moment at point C is bigger than the moment at point B. So we begin by distributing the moment at point C. So first of all, we shall calculate the moment that is to be distributed at point C. So remember that we say that to do that, we pull out the joint. That is, for this case, it is joint C, like that. So this is joint C. Then the moment we are finding, we give it a positive direction, that is clockwise M. Then now we look at the moments at point C. We've got 100 that is acting on the left hand side, but in the clockwise direction. But remember that we say that as we are drawing it on this side diagram here, we draw it with an opposite sign. If this way it is positive, here we draw it with a negative. So positive is for clockwise and negative would be for anti-clockwise like that. So here we're having 100. Therefore my m, when I sum up the moments at that point, it would be m is equal to 100, which is a positive, like m minus 100 is equal to 0. I get m is equal to 100. So my moment will be distributed md would be equal to negative m, that's equal to negative 100, like that. So that means that I need to distribute a moment of what? A moment of negative 100 at point C. So let's try to do that, and then we see how the work is done. Just before we begin the work of the distribution, remember that we need to come and add our distribution factors above the diagram. If you remember, the distribution factors that we are calculating at point B we had MB at 0.4, then still at point B we had mu BC at 0.6, then at point C we had mu CB at 0.667, then mu CD was 0.333, like that. So adding those ones on our structure, we would be having 0.4, 0.6, then 0.667, and then 0.333, like that. Then we say that we are first of all distributing the 100, negative 100, just from what we had calculated previously. Then let me just create a boundary in the middle here. So when you begin a distribution at point, let me use a different color, let me use a black. Okay, so when you begin a distribution at points here, we take negative 100 times 0.333. I would be having a negative 33.3. Then negative 100 times 0.667, I get 66.7 negative. Then we say that between B and C, when B and C are clamped, we do create fixed ends at B and C. So that means that we can what? We have got a transfer factor or conveying factor over half. So I come and I half this, and then it will be giving me a negative 33.4 at point B. So, and then now, like when you look at this other end, the end CD, like CD, since it has got a fixed end at C, and then a free hinge at D, it cannot transfer because the carrying factor is a 0. So now, like after doing that, we cannot transfer anymore. Now we need to come and look at point B, evaluate the moments there, and then we distribute them. So to find the moment to be distributed at point what? At point B, we follow the same procedure that we did to find the moment to be distributed at the point C. So we have to come and isolate out point B, like that. Point B. Then at point B, we are having a moment of 60. This one here, that is positive. That means on this diagram here, we shall draw it acting in the anti-clockwise direction by the end of the left hand side. So here we shall be having, let me change the ink. We shall be having a 60. Then the moment we are trying to give it a positive sense, that is M. Then we also have 100, but negative. So that is for the moments on the right hand side. 100, but it's a negative, so we give it a clockwise direction, since we say that the direction of the moment is altered from the one which is given at the end point. So that implies that that now that implies that in this direction here we shall be having 100. Then at the same point we have added on another moment which is of magnitude 33.4, so it's carrying a negative, so we also come and add it to that of 100, so we're also having a 33.4. So we come and find the summation of, we come and evaluate the value of m by summing up the moments and equating them to 0. That we shall find that our m would be equivalent to a 60 minus 100, then minus a 33.4. That would be giving us a value of negative 73.4, like that. Then my MD would be the negative of that value, so this becomes a positive 73.4. So the moment to be distributed at point B would be a moment of value 73.4, like that. 73.4. So now next we come and distribute that moment. Let me use a different ink for this case. Distributing moments at point B, we come and take the 73.4, then times 0.4. What do we get? We get a 29.4. We get a 29.4, like that. Then when I multiply the 73.4 times 73.4 times 0.6, I do get 44.0, like that. Yeah. Then I know that at A and then at B, when these ones are when B and C are clamped, I'll be having a distribution factor of a half at this point, since we after clamping this becomes a rigid support. Then here we have a carrying factor of a half. So when I do that, this would be conveying a value of 14.7. Then even between B and C, we've got a conveying factor of a half, so times a half. Then we add another moment at point C, that is a moment of 22. So that means that point C has got a new moment that also now needs to be distributed. But now before distributing it, we no longer undergo the same process that we did of pulling out point C and then calculating the total moment existing there. Now we know that the total moment that hasn't been distributed is only 22. So what we do, we simply multiply the 22 by a negative sign, then we distribute it again. So let's do that and see what we get. So when you multiply this by negative, we get negative 22, then times 0.333, we come up with a value of 7.3, like that. Then negative, then negative 22 times 0.667, we get a value of negative 14.7, like that. Then between these two, we've got a distributing factor of a carrying factor of a half. So multiplying this by a half, I get a negative 7.3, like that. Then we discover that then actually at this point here, towards from point C to point D, we don't have a carrying factor, so therefore there's no in which we can carry the moment to point D. Now we come and see that point B has got a new moment. What do? We multiply it by a negative sign and then we distribute it again. So multiplying it by a negative sign, it becomes a positive 7.3, and then positive 7.3 times 0.4, I get a 2.9, like that, a 2.9. Then positive 7.3 times the 0.6, I get a value of 4.4. Then between point A and point B, we said we have a carrying factor of a half, so times a half, I get a times a half, I get a value of 1.5. and then from this point here at point B towards C, we also have a carrying factor of over half. So towards this way times a half, I get a 2.2, like that. Then we see that point C has again got another moment here. Now a person might ask that for how many times have we got to continue with the procedure? Because we see that every after dividing we get a new value of moment here. Usually after carrying out the distribution 3 times, we get a value that is almost accurate. So so far we see that we've done our distribution twice, so we can go on and distribute for the last time, and then yeah, we shall be able to now finalize our calculation. So now here we're having a new moment negative 2.2. So what we will say that for us to distribute, we multiply this by negative to get a distributing moment. It so it becomes negative 2.2. Then when I distribute it, I would be having negative 2.2 times 0.667, giving me a value of negative 1.5. Then the same value, negative 2.2 times 0.33 gives me a negative 0.7, like that. Then between C and B, I have a carrying factor of a half. So when I carry it by a half here, I'll be getting a new moment at point B that is equivalent to negative 0.7. Negative 0.7, like that. So what I do, I now have to multiply by negative half, and then I distribute it. So negative 0.7 by half, I get a 0.7. So negative, then after getting that, I now have to redistribute. So negative 0.7 times 0.6, what do I get? What do I get? I get a 0.4. Then onto the other side, I get a 0.3. Then towards B, from B to A, I have a distribution factor of a half. So this one, it carries up a value of around 0.2. So since like this is now our third time, like this one here was our first time, this was the second time, now this is the third time we are distributing. Now we can end there. So that means there is no need for us to carry on this moment onto point C. So after doing that, now we come and find the summation of the moments at the respective points, like point A, point B, and then point C. Now we want to come and sum up the moments here. These ones, these ones, these ones, and these ones here. So beginning with point A, I add up from negative 60, 14.7, 1.5, and 0.2. I come up with a value of negative 43.6. Then when I add up the values at point B, on the left hand side I have a 60, 29.4, 2.9, and then a 0.3, I get a value of positive 92.6. Then on the right hand side of point B, when I add up negative 100 minus 33.4 plus 44 minus 7.3 plus 4.4 minus 0.7 plus 0.4, I get a value of negative 92.6. Then I do the same at point C. At point C, beginning from 100 up to the negative 1.5. When I add them up, I'll be getting a 41.3. Then when I do the same addition on the right hand side of point C, negative 33.3 plus negative 7.4 plus negative 0.4, I get a negative 41.3. So after doing that, I can now move on and draw my bending moment diagram. So I come back and I redraw my span. like that. Then we say that this is okay. Let me label them A, B, C, and then D. So before we put these values that we found on the diagram, it's better that when you first come and decide on the signs that you're to work with at each point. So if this is point A, then this is our point B, and then this is our point C. Then at point A, I can leave it because I know it's a 0, there's no moment, but for the sake anyway, let me put it there. So like we know that at point A we have a moment of what? Of negative, a moment that is given by negative 43.6. So we're saying that if we are to draw it on the bending moment diagram, we have to like change the sign to a positive, which is negative. So negative becomes a positive. That means positive is for clockwise. Therefore, clockwise, that means the upper part is under tension. So that's how it will be with a value of 43.6. And when you come to point B, we've got a 92.6 that is on the left hand side, implying that is clockwise. So when you come to this final bending moment diagram, we have got to alter the sign to become a clockwise. So it takes on this direction. Then on the right hand side it is negative, meaning that it's turning towards, it makes it turn towards the anti-clockwise. So altering the sign, it turns to clockwise. Then since the signs on point B are the same as the signs on point C, that means the arrows would be of the same pattern like that. And then lastly, here we have a 0, so I don't have to mind about it. So therefore, I now come and I begin my plotting. So at point A, we are saying that we have a moment that causes the upper part to have tension, and then the moment is a value of 43.6. Upper part in tension, that means my bending moment diagram should be on the upper side, assuming that is 43.6. Then we come to point B, upper part, like we say that the upper part is under tension. So our peak value would be somewhere here like that, a value of 90, a value of 92.6. Then lastly at point C, it is still all these two cause the upper part to be in tension with a value of 41.3. So if now we come and look at the corresponding spans and then see whether they had forces or not. If they had force initially, we first connect with the dotted line, then we superpose the action of the corresponding force on. So if we try to look at like our first span AB, we see that there is action of a distributed load. So what we do, we first connect this AB, the values with a dotted line like that, with a dotted line. Then we come and superpose the bending moment diagram of a distributed load, which is like that, semicircle. So we'll be having something like that. Then let me draw it more better. We said we first add a dotted line, then we come and superpose our diagram like that. Then we look at the span BC. BC has the action of a concentrated load, so we also first come and join the points with a dotted line like that. Then we superpose the bending moment diagram of a distributed load, which is like that, a triangle. So we come and superpose it with a maximum in the middle of the span. And then lastly, when you look at our point C, there is no force acting, so simply we just come and connect the value here up to the hinge, because you know that the moment at the hinge is equal to 0. So for this example, our final bending moment diagram is as shown here. Our next example is as shown on the screen, and for this example, we also require us to use the bending moment distribution method, to draw the bending moment diagram of this system. And then unlike the other two previous examples we looked at, this structure looks to be more complicated. And then we see that it also has the I varying on each and every span that we are having. But nevertheless, the steps of calculations are the same, and we shall see that it's not that much hard and it's still similar to the previous examples that we looked at. So to begin with, let's begin by okay by making it somewhat simple. Yeah, you can do that by letting let us let our EI be equal to a 1. Yeah, that's just for simplicity in calculation. Yeah, so we say that the first step in using the moment distribution method is to find the linear bending stiffness of the system, that is the small I. So again, by finding the small I, so as we think about finding the small I, remember that we say that we need to add clamps at the various joints. Like for example, at B, then at C, we can add clamps and then we form the various spans. We have now got span AB, span BC, span CD, then span B. So here we have got an E. We have an E here and then an F here. So we also have span BE and then span CF, like that. So let's first begin by dealing with the eyes. So we say that for the sake of AB, we shall be having IBA would be equivalent to we are having E then times 4I, that is divided by the length, which is a 4. That like the 4 and 4 cancel, so leaving us with only EI, and then the EI will let it to be equal to 1, so this would be equal to 1. Then when you move to the span BC, we would be having I BC being equivalent to, that would be 5E I, like E times 5 gives us 5EI, then divide by its length, which is a 5, which also gives us a value of 1, the 1. Then we go on to span CD. So we shall calculate our I CD as being equivalent to 4 EI then you move on to the next span, that is span BE. So our I BE would be equivalent to, that is 3I times E, that is 3EI. Oh, sorry. Before that, okay. ICB was equal to 4 EI divided by its length. Its length was a 4. Its length was a 4. This is supposed to be equivalent to a 1. Then you go to IBE. This would be equivalent to 3 EI. Then over 4, this would be equal to 3 over 4, like that. And then lastly, we go to span CF, giving us ICF. This is equal to 3 EI, then over 6. This is equal to half, like that. Then after doing that, we now have to go on and also find we have to find the bending stiffness next for each of the spans. So we know that the bending stiffness, so having found the having found our linear bending stiffnesses as shown here, next we are going to move on and find the bending stiffness. This is the linear bending stiffness, so the next we find the what? We are going to be finding the bending stiffness, that is abbreviated by letter S. So we know that if at all we look at our span AB, so if at all we do add a clamp at point B, we shall be having a bending stiffness that moves from B towards A, that is SBA, then from B towards C, that would be SBC, then from B towards A, that would be SBE. Then likewise at point C would be having, when C is clamped, we would be having bending stiffness SCB, then SCD, and then SCE, like that. So let's evaluate one at a time and then see what we get for each. So for the sake of AB, our SBA would be equivalent. We know that that point B would be a fixed end, while point A is a hinge joint. Therefore, our bending moment, our bending stiffness would be a 3 IAB, as we said earlier on. 3, we'll be having 3 IAB, of which our IAB is equal to a 1. Our SBA would be equal to 3 IBA, of which IBA is equal to 1, so this gives us a value of a 3. Then we move on and find that at BC. So our SBC, which is also equal to the SCB, all these two are equal. So I'm just calculating them at once. That would be equivalent to what? Would be equivalent to it would be equivalent to 4. To be equivalent to 4 IBC. That is because we are having, if let's say we are dealing with a point B, B clamped. If we look at our SBC, B would be clamped and then C clamped. If all these two are fixed supports, we say that the bending stiffness is 4I. So that's why here we have it as 4IBC. So our IBC is equal to 1, so this gives us a value of a 4. Then you move on and find the next. After IBC, we go to our SCD. Our SCD, between C and D, we have a rigid support, and then we've got a hinge support. So that one there would be giving us a value of 3. A value of 3I, a value of 3I CD, 3I CD, that is equivalent to our CD is equal to 1, that gives us a value of a 3. Then we go on to BE. So for the sake of BE, we have a fixed end and then a fixed end. So our bending stiffness SBE would be equivalent to 4IBE, that is equal to 4 times 3 over 4. That would be equal to a 3. Then next we need to find that one of CF. So SCF would be equal to CF. We also have a fixed end and then a fixed end here. So it's also a 4 ICF is equal to 4 times ICF. ICF was a half. That gives us a value of a 2, like that. So having found our corresponding bending stiffnesses, next now we have to come and find our distribution factor. So still doing it on the same surface here, so as we have visibility of all the results. We'll begin by dealing with point B. So at point B, we find the summation of the bending stiffnesses. At point B, we have 3 of them. I will say that we have SBA, SBC, and then SBE. So these would be equal to SBA plus SBC, then plus SBE. This would be equal to 3 plus 4 plus a 3, which is equal to a 10. Therefore, now we come and find our mu BA. Mu BA would be equal to our SBA divided by a 10, divided by the summation, divided by which is 10, so that would be 0.3. 0.3. Then you move on and find the next mu BC. Mu BC would be equal to our SBC, which is a 4, divided by the summation of S at P. That would be giving us a 0.4. And then lastly, we would be having a mu BE, which would be equivalent to SBE, which is a 3, then divide by 10, that would be a 0.3. So at point B, we are having these 3 distribution factors. Next, we come and look at point C. So at point C, we would be having that's point C. So at point C, our distribution factors would be giving us a sum of summation S at C would be equal to, that would be SCB, SCD, and then SCF. It should be equivalent to SCB, then plus SCD, then plus SCF. This would be equivalent to 4 plus 3 plus 2. This is equal to a 9, like that. Then you move on and now find our distribution factors mu CB. This would be equal to mu BC. We need to take our SCB. Our SCB was equal to a 4, then divide by the summation, which is a 9. That gives us a value of 0.445. Then our next, which is mu CD, this would be equal to SCD. SCD is a 3, then divide by our summation of S at C, which is 3 over 9. This gives us a third, which is equal to 0.333. And then lastly, we have the mu CF. which is equal to 2 over 9. This is equivalent to 0.222, like that. So we've found our distribution factors, our bending stiffnesses, and then what we are left with is to find the bending moments at the corresponding fixed ends. Now for the endpoint moments, if we observe well, we can see that we've got some spans that do not carry any load. That means that they won't be having any value of endpoint moment, like the endpoint moment would be equal to 0. So for example, like span BE, span CF, and then span CD. So the spans that we shall have to deal with are spans AB and then spans BC. So for these spans here, we see that all of them are under distributed load of magnitude 20, and then one of them is having both ends fixed with a rigid support, while the other one is having a rigid support at B, while at A it is a hinge support. So we need to move to the table and then look at the formulas of calculating the fixed end supports. So if you observe for the one which has got the fixed ends, that is the span BC, we see that the formulas are MAB, that is for the, now for the other side it should be MBC would be negative QL squared divided by 12, then the MCB would be QL squared divided by 12. Then the next one is this one here of this nature, having distributed load, but just that the directions are just inverted, as in like point, it's supposed to be A with a what, with a point A having the hinge, while B has got a fixed support. So the formula is negative QL squared divided by 8. So let's move on and do the calculation. So we move on and do the calculations. We say that for the sake of the span, that is AB, we only have the endpoint moment MBA, that's given by QL squared over 8. Then there is also one thing that we need to observe, that the positions of the supports have been alternated, and then like from the table that we just looked at, all these moments that have been given, they carry on a sign that that anti-clockwise direction, or the anti-clockwise moment, is positive, and then the clockwise is negative. Now like when you look at if we look at point what, if we happen to look at this one here, like the moment MAB, when you see the way like it turns, it would be turning like that. That is in the clockwise direction. That's why it has got a negative here. But now when you go back to our system, if you go back to what we've been given in the question, we see that our moment MBA would be of this nature here. MBA would be causing the system to turn in the anti-clockwise direction. Therefore, instead of writing it with a negative, we write it with a what? With a positive. So our moment MBA would be equivalent to QL squared positive, because of the reason that we said, QL squared over 8. This would be equal to, our Q was a 20, then times our L was a 4 squared, then divide by 8. This gives us a value of 40 kilonewtons per meter, kilonewtons meter. Then now we move on to calculate that of part C, and then the span BC. Yeah. So at M, so for the sake of the MBC, like Look at the MBC. MBC would be causing the structure to be turning in the clockwise direction like that. Then the MCB would be causing the structure to be turning in the anti-clockwise. Therefore, the MBC would be a negative since it's clockwise, and then the anti-clockwise would be a positive, just as it was in the table the other side. It won't have any change in sign. So from that, our MCB would be equivalent to negative QL squared, then divide by 12. This would be equal to negative 41.7 then that means that now our MCB would be equal to a positive because they only have a difference with the sign, 0.7 like that. So now after doing that, we can now move on and carry on our moment distribution. Yeah, so if like this is our structure, now we have to come and add on the distribution factors that we had calculated above. So if you go back at our distribution factors were as follows. We had BA 0.3, BC 0.4, then BE 0.3. Then for the sake of those at point C, we had 0.445, CD 0.333, then 0.222. So we come and add those onto our structure here. Yeah, so after adding on our distribution factors, we would be having a structure as shown here. So we have also added on the endpoint moments. We found our MBA as 40 on the left, that's BA. Then we had the MBC, so I've written it as negative 41.7, somewhat like away from this road because I want to put the distribution factors, sorry, the distributed moments for the BE close to BE itself. So I had to leave some distance in between. This is E, yeah, like that. So then for the sake of MCB, it's also 41.7. Now after doing that, we now have to come and find the moment to be distributed. Now for us to find the moment to be distributed, we need to look at point C and then point B. Then we determine which one has got the highest value of moment. So when I add the moments at point B, I have 40 minus 41.7. I remain with only 1.7, negative 1.7. And then at point C, I will be having a moment of what? A moment of 41.7. So meaning that the moments at point C, the moments at point C are bigger. Therefore, I begin by distributing the moments from point what? From point C. So I need to first pull out point C and then work out the moment that I'm supposed to distribute. So if I feel like this is my point C, if this is my point C like that, it's a rigid support like that. If this is point C, and then say the moment we are looking for, say it's known by a value M in the positive direct clockwise, which is positive, then we are having the action of 41.7, that is on the left hand side, and then here it is a positive, meaning that the action is supposed to be taken as that in a clockwise direction. But we say that when you're adding it on this extracted figure, we draw it in the opposite sense of the sign here. So if this is clockwise, this we are supposed to draw it as anti-clockwise. So therefore, we would be having something like that with a value of 41.7. So my M would be equal to 41.7. That is when I sum up the forces at that point. Therefore, my moment to be distributed MD would be equal to negative M, which would be equal to negative 41.7, like that. So I would first of all need to distribute that moment of value 41.7. So I come and I write it at the top of this. I have a negative 41.7 to be distributed like that. So when I come and I multiply it by 0.333, I change my ink. Let me say that let me use which color? Let me use black. I get a negative 41.7 times 0.333. I get a value of negative 13.9. Then I come to CF. Let me lower it a little bit. I come up with, just a moment, the value of negative 13.9, like that. Then when I come to CF, for CF let me use a different color, so that for CF let me be using this light green. So for CF it would be 0.22 times negative 41.7. I get a value of negative 9.3. Negative 9.3. Then for the sake of CB, that is negative 41.7 times 0.445, I get negative 18.5. Say that for that I'm using which color? Let me say that I use a yellow for it, so I get a negative 18.5 for that. Just that these points are not appearing clearly. Yeah, that's a point in between. Then also here we have a point in between. Okay, so having done that, we move on with our work. Let me see what other color can I use. Okay, let me try this one. So between now, like transferring from C to B, we know that here we are having a what? A carryover factor over half, because we are having a fixed point at B and then a fixed point at C. So when I transfer that first by half, you would be having a negative 9.3. Like that. So that now brings us to what? That now brings us now to point B. So after reaching point B, now we see that now we're having three moments. We have a 40, we have negative 40.1, and then negative 9.3. So we are supposed to also calculate for the moment that is to be distributed at that point. So what we do extract out that point B. So assuming that this is our point B, like that, then the moment that we are to calculate, we give it a clockwise sense, that is moment of value M, and then we have a 40, we have a moment of a value 40 that is on the left hand side. So since it's positive, that means when you're doing it on this extract, we give it a negative sign that makes it act in the anti-clockwise, opposite to what we had here that was clockwise. So this we have a 40, then the negative 41.7 here, and then negative 9.3. These two are acting in the what? Are acting in the anti-clockwise. So that means we need to turn them to act clockwise, and thus the arrows would be like that. I would be having a 41.7 and then 9.3. So my M would be equivalent to, would be equal to 40 minus 41.7 minus 9.3. This gives us a value of what? A value of 11. That is a negative. Therefore, my MD, the moment to be distributed, would be equal to a negative of M. That would be equal to positive 11. Therefore, we have to distribute a moment of 11 at point B. So now, if we take that 11, oh, I'm running out of colors. So now we take the 11 and then multiply it by what? By 0.4. We get what? We get a 4.4. We get a value that is equal to 4.4. Then we multiply it up to the next. If we take the 11 and multiply it by 0.3, we get a 3.3. Then when we take the same 11 and multiply it by 0.2, we get a 2.2. Then between the B and A, we've got no carrying factor, so therefore we don't carry up this load this way since the carrying factor is equal to 0. But now between now B and C, since this is fixed and then this is fixed, the carrying factor, therefore this 4.4 has got to be carried over to what? This 4.4 has got to be carried over to point C. So once carried over, once carried over, it would be giving us a value of what? A value of, this would be a 2.2. A value of 2.2, like that. So since it is a value of 2.2 that we are having, that means point C has got a new moment, so we need to distribute it again. So what do? We say that if you have a new moment, you simply multiply it by a negative sign and then distribute it using the corresponding ratios of distribution that we found. So when you multiply it by negative, we get a negative 2.2. So we begin distributing negative 2.2 times 0.33, that gives us a value of a value that's equivalent to negative 0.7. Then negative 2.2 times 0.222, that gives us a value that is close to negative 0.5, like that. Then negative 2.2 times 0.44, it gives us a value that is close to what? That's close to a negative 1, like that. So then we say that between from B to C, we've got a carrying factor of a half. So therefore, that moment is again carried towards what? It's carried towards point B. So when carried towards point B, it's carried and then it becomes a value of negative 0.5, like that. So point B has now gotten a new moment that needs to be distributed. So we multiply this by negative, it becomes a positive 0.5, and then multiply it by the distribution factors here. So that would be giving us let's say if we begin with this side of PA, 0.5 times 0.2, that would be giving us a value that is close to what? That is close to 0.15. Then when I multiply it with that of BE, that is 0.3 times 0.5, that gives me a value that, yeah, that is also 0.15. What color was I using there? 0.15. This one has a point in between. There's a point in between there. Yeah. And even this. Yeah, so 0.5 times 0.4. 0.5 times 0.4. That would be giving me a value of what? Of a value of 0.2. 0.2, like that. And then for this one, we shall just stop at two sets of values, that is this one and then this second distribution, like that. So after doing that, now we come and find our what? We come and find our summations. So when I sum up the forces, so when I sum up the moments, I would be having, for the sake of this side, a 0. For the sake of this side, okay, just a little correction. I'm realizing that we made some little mistakes somewhere here. This is supposed to be a 0.3. This is supposed to be 0.3. Thus, this value also is then supposed to change to a 3.3. 3.3, like that. So in that, when I add up these values, I would be coming up with a total of, that is 40. That is a total of that would be 43.4. Yeah, 43.4, like that. Then on these ones, when I add a 3.3 plus 0.15, I'll be getting a 3.45. Then when I come to these ones here, those ones of BC, that is from negative 41.7, negative 9.3, 4.4, negative 0.5 plus 0.2, I would be coming up. I would come up with a value of. I would come up with a value of negative 46.9. And then when I add up 41.7, negative 18.5, 2.2, negative 1, that adds up to a value of 24.4. 24.4. Then on the other side, C, it adds up to a value of negative 9.8. And then these ones, these two add up to a value of negative 14.6, like that. So we are not yet done, because remember that our point B, our column BE has got a fixed end up and then a fixed end here. So there is also a distribution factor. Sorry, not a distribution factor, a carrying factor that we never put into consideration, that now we need to work on right now. Okay, so for the sake of doing that, for the sake of catering for that carrying factor that we never considered, yeah, let me use this. That is for the sake of EB and EB, that is so faint. EB, and then FC. So what we do, I will see that there was a moment that had to be passed on from BE to EB, and then since we shall be having a fixed end, since we have a fixed end at this point and then a fixed end at this, so the factor would be a half. So that implies that I need to get the moments that were on BE and multiply them by a half and then write them under EB. So this one here times a half, I would be getting a value that is close to 1.6. Then 0.15 by a half, I get a value that is close to 0.1. Then when I come to CF, I do the same. CF transfers to FC, and then we've got a rigid support at C and then at F, so the factor would be a half. So I take negative 9 times a half, negative 9.3 times a half, I get a negative 4.7. Then negative 0.5 times a half, I get a value of negative 0.2. Then after doing that, I now come and I add them up and I also get the total there. So for this I would be getting a 1.7, then for this I would be getting a 4.9. So having found entirely all the moments that are required, I now can go on and draw the what? I now can go on and draw the bending moment diagram that I need. Let me just make the decimal places more clear. Sorry, yeah, we have a point there, even there, there, and here. Yeah. So having found my moments, I now can move on and draw my bending moment diagram. Okay. So we are going to draw the bending moment diagram. And as we had said earlier on, what we are going to do, we are first going to pull out the corresponding joints. We first pull out, let's say, the joint at point B, and then we have the joint at point what? At point C. This is B. Then we have that at point like this is C, and then we have that at what? That at E, and then that at what? And then that at F. So now, looking at the kind of moments that we have at point C, so at point B, on the left hand side, we have a value of what? We have a value of 43.4. That is positive, meaning that it is clockwise. So we say that when you're drawing it onto the actual bending moment diagram, you have got to change its sense. If it was clockwise, it turns to anti-clockwise. So this is positive, so it was clockwise, meaning that it's supposed to be clockwise like that. So the upper part would be under tension. Then when you come to point, you're still at point B, but now dealing with BE. We have a value of 3.45 in the clockwise since it's positive, but now when you're drawing it on the final bending moment diagram, it means it will be in the anti-clockwise. Then lastly, we have a negative 46.9, that is on the right hand side. Negative means is anti-clockwise, so drawing it on the final bending moment diagram, it takes on that direction there of clockwise now. Then we look at point E. At point E, we had a positive that is 1.7, meaning that's clockwise. So drawing it on a bending moment diagram is supposed to be counterclockwise. So counterclockwise, that means it's supposed to be a moment that causes this side to be under tension. Then, okay. Then we look at point C. So looking at point C, we have a value of 14.6 in the negative, which is negative, meaning that it's anti-clockwise. So drawing it on a bending moment diagram, we draw it as a clockwise. Then looking at CF, we have a negative 9.8, that is anti-clockwise. Drawing it on a bending moment diagram, we draw it as a clockwise like that. Then looking at this one here on CB, it's a positive, that is 24.4, meaning that it's clockwise. Thus we draw it as anti-clockwise. And then lastly, we look at point F, we have a positive 4.9. That means that it is acting in the, actually this is supposed to be a negative, yeah. yeah, it's negative 4.9, so it is acting in the anti-clockwise, so we draw it as a clockwise, yeah, like that. So we are going to transfer all these and then use them as aids to determine what side is under tension. So looking at point B, at point A, this is A. Okay, let me just relabel the drawing again. Let me label. We have this as A, this one here as B, C, D, E, and then F. So looking at our point B, we have the moments as shown here, point B. This on this side, we have a moment of 43.7, causing the upper part to be under tension. So we mark it there, 43.7. Then at the same point, we do have a moment on this side that is given by negative 46.9, still the upper part under tension, like that. So we have got two points there. Then we have a moment, this one here, that is at 3.45, causing the left hand side to be under tension. That means, let's say we mark it from somewhere like that, yeah. And then we look at point E, a moment of value 1.7, causing the right hand side to be under tension. Let's say it's somewhere there. Then now, like since the rod, since at B, E, B, and then at E we do not have any force, we can just now draw these as a straight line like that. Then for the sake of AB, at AB we had a distributed load, so therefore we first connect up this portion as a dotted line like that. Then we come and superpose the diagram like that. And then now we continue with point C. So at point C, we have a moment that causes the upper part to be under tension. That is side CB. CB, that was with a value of 24. With a value of 24.4. Let's say it's up to somewhere there like that. Then this side on the right of point B, we have a value of negative 14.6. Let's say it's somewhere there. Let's say it's somewhere there like that. And then when we come to the CF, at CF we do have this one, causing the right hand side to be under tension with a value of 9.8. Let's say 9.8 is as small as that. And then lastly at F, we have a moment of value of negative of 4.9, causing the left hand side to be under tension. So let's say it's something like that. So since we don't have force along CF, we just come and join it as a straight line like that. Then even at CD, we don't have any force acting, so we just come and join our moment as a straight line. Then at BC, we come and join. We first join using a dotted line since we have the action of a distributed load, like that. Then afterwards, we come and superpose our bending moment diagram like that. Then after doing that, we now come and add the values of the moments at each point, and that will be it. So after adding on our values of the moments, our final drawing would be something like this here. So that's how we use the moment distribution to solve such a number. Thank you.